Hey everybody, welcome to our 37th installment in our series on vertex operator algebras. Last time we introduced the twisted vertex operator as a solution to a particular operator equation. And this time we'll demonstrate that it is the unique solution. Well, at least unique up to an overall scalar. So let's get started with a quick review of what we're even talking about here. We are trying to find operators associated to the roots sigma plus or minus of the sigma 1 twisted affine Lie algebra SL2. These operators should satisfy the following operator equations, where h of m is some generic operator in the Cartan subalgebra of SL2, promoted to a degree m operator in the affine algebra. Alpha, of course, is a fixed member of the Cartan subalgebra. Of course, as an aside, for SL2, the Cartan subalgebra is one-dimensional, but we're trying to highlight the structure here that we'll be dealing with for more complicated cases in the near future. The second of these equations is essentially the condition that D act as a degree derivation. Now, last time we formed two formal series of operators, E plus and E minus, of alpha and z, and combined them in such a way that x of alpha and z is the well-defined generator in the formal series of endomorphisms of the Heisenberg module V that solved the alpha-formation equations. Today, we will show that x is the unique solution, well, again, unique up to an overall scalar. More precisely, we follow FLM in claiming that any operator in the formal series of endomorphisms of V that also solves the operator equation here is of the form A times E minus times E plus minus alpha and z. Sorry, there should be minus signs before those alphas. Here, A can be any scalar in the field F. Proof. Suppose W of z does indeed solve the operator equation, and then define the operator z of z as E minus WE plus, which evidently is well defined on the endomorphisms of V because the rightmost factor of E plus, as discussed last time. Now, we can expand z in terms of the operators of degree n, and clearly the degree derivation works as it should. Now, because W of z solves the operator equation from the claim, we will show that z of z commutes with all other h of m. To that end, consider the commutator of h with z, which by definition is the commutator of h with E minus WE plus. Let's begin the computation by expanding the commutator. For now, let's suppose that m is greater than 0. So in particular, h of m commutes with E plus, as E plus only depends on positively graded operators, as discussed last time. Simultaneously, we can commute h through E minus in the first term, and combining these terms together gives us two terms, both with commutators with respect to h. Now, since W of z solves the operator equations by hypothesis, we know what its commutator is with h. We also know what the commutator of h with E minus is from our discussions last time. Evidently, the two terms cancel each other out, implying that h of m commutes with z of z. The logic for m less than 0 follows similarly. So, z of z commutes with all operators h of m associated with the Cartan subalgebra H, and therefore it commutes with everything in the underlying Heisenberg subalgebra of SL2, which form the basis of our module V. Because of this, and the fact that V is an irreducible Heisenberg module, z of z must be a scalar, as you might recall from our discussion of Heisenberg modules in episode 15. Hence, E minus WE plus must be a scalar, which you can easily invert to find that W of z equals A E minus E plus. So we're done. Now, this claim implies that if the twisted affine Lie algebra SL2 has a representation on V, the operators sigma plus or minus must be represented by the vertex operators x of plus or minus sigma and z. Note that sigma plus may be chosen to be either of plus or minus x of sigma and z, which begins to explain the normalization factor out front. Of course, it remains to show that the commutator of x alpha z with x minus alpha z is given by the following. which of course is the subject of our next few lectures. And that's our show. Next time, we'll start laying the groundwork to prove that the twisted vertex operators are used in the representations of SL2 of sigma 1 on V, and hopefully motivate those details with our earlier discussions of algebraic quantum mechanics. Thank you so much for watching. See you next time.